Hello everyone, thanks a lot for watching this video. Today I want to talk about the communication complexity of the submodular maximization and its application to streaming and robust setting. And this is a joint work with Mohan Feldman, Ulla Svensson, and Rico Zanklausen, and I'm Ashkan Norzifard. Let me start by defining the problem. In this problem, we are given a set function f that returns a positive value for any subset of a ground set W. We call it monotone if adding any element to any set increases the value by at least 0, so it cannot decrease. If it only increases, we call it monotone, and for monotone functions, we call them submodular. If adding an element to any set, the improvement that it gives is less than adding it to any of its subsets. We call this the diminishing return property as well. So it looks like a log function, basically. Okay. So this problem has been studied in different settings, distributed, streaming, and offline setting, and under various constraints like Cardinality Constraint, matroid constraint, knapsack constraints, and others. But maybe the most famous one is the Cardinality Constraint. It has been also benchmarked for designing new algorithms and coming up with new techniques. So in this work, we focus on the Cardinality Constraint. In this problem, the goal is to find a subset S such that the size of S is at most k, so we can just pick k elements. And the goal is to maximize f of S. And a special case of this problem is the k coverage problem. In the k coverage problem, we are given some sets over the entire ground truth, and we want to choose k of them, covering the maximum as much as possible from the ground truth. So here is an example, and if you're interested in the sets of size 2, the optimum solution is the green one on the top and the purple one on the bottom. And it covers 11 elements, so the value of the optimum solution in this case is 11. Okay. This problem has been studied in the offline setting from 70s, and it's known that 1 minus 1 over E is tight. It has been a line of research has been dedicated to this work in the machine learning community as well, due to its various applications, for example, influence maximization on any type of summarization, image summarization, dot summarization, and so on. Due to the large size of the data, the distributed setting and streaming setting has also attracted a lot of attention, and it's known that 1 minus 1 over E is tight in the distributed setting as well. But it's remained to get a tight answer for the streaming setting. It was known that the gap between 1/2 and 1 minus 1 over E in the streaming setting, in a very recent work, Huang et al. Showed that the upper bound of 0.58. So basically, no algorithm can achieve better than 0.58 in the streaming setting. And in this work, we show that 1/2 is tight. Let me give a general overview of our approach. First, we focus on two-player communication and show tight results in there. And we show that we use the algorithm for two-player to design similar bounds for the robust submodular maximization. And later on, for achieving the tight 1/2 result for the streaming setting, we studied the multiplayer communication and showed that if we have basically k players, one cannot achieve better than 1/2. Okay, let me start by defining communication complexity, in particular for two-player game. So we have Alice on one side, we have Bob on the other side, and the goal is to find a solution with, for the entire input by sending message between Bob and Alice. So Alice has some part of the input, Bob has the rest of it. They communicate messages between each other, and the goal is to get a good solution. One-way communication is the case that Alice can only send message to Bob, and based on that message, and of course the elements that Bob has itself, Bob should output the final solution. In particular, for the case of submodular maximization, Alice has given some part of the input A1 to AA, and it has access to an Oracle F that it can query the value of any subsets of her input. And similarly, Bob has some part of the input and access to Oracle F. And Alice will send a message to Bob. This message can be anything, can be elements, can be some 0 or 1 bit strings. And based on that message and the elements that Bob has, Bob should output the final solution. The main two interesting parts for this problem, we have two objectives basically. The first one is the quality of the solution. We want the final solution to be comparable with the original with the best optimum solution, for example, within a factor 2, 10, or something like that. And also the length of the message in here is very important. We want the message to be as short as possible. In this work, we show that for the two-player setting, 2/3 is the correct answer if the memory is between k² and n/k. So basically, we present an algorithm that uses the length of the message is k², and also show that any algorithms that wants to achieve better than 2/3 must use memory basically at least omega of n/k. We also show that if we are okay with losing a factor epsilon in the approximation guarantee, one can reduce the memory of the algorithm to k log k over epsilon instead of k². And so one of the applications of the algorithm that we introduce is in the robust submodular maximization setting. Let me just define the setting first. In this problem, in this setting, we are given n elements, E1 to En. First, an algorithm should output a subset of this element, which we call the intermediate solution, E'1 to E'. So first it finds these elements. Then an adversary deletes of these elements. And now the goal is to output a subset of size at most k from the remaining elements. So basically, the final solution S should be the subset of the intermediate solution minus the solution that is deleted. And the goal in here is to have, first of all, a good solution, of course, and and also we want to minimize the size of the intermediate solution as well. The smaller, the better, of course. There's a line of work dedicated to this problem, and the best known result is a 1/2 approximation that uses memory. The length of the intermediate solution is d plus k. In this work, we improve the 1/2 barrier to 2/3, and we present a 2/3 approximation, basically by just extending the algorithm that we have for the two-player case. And the size of the intermediate solution is dk. We also show that if someone is interested in only polynomial runtime algorithms, one still can achieve better than 1/2, and we present a 0.51 approximation algorithm in this case as well. In order to get the result for the streaming setting, we generalize our techniques to the p-player setting. So what's the p-player setting? Again, we have p-players, p1 to pk, for example, and each of them will send a message to the next one. Again, it's one way, so the first player sends to the second one, second to the third one, and the final player should output the solution. We show that 1/2 is tight in this setting as well. It was known that there's an algorithm that the length of the message is from O or K, and in this work we show that any algorithm that achieves better than 1/2 should use a memory of at least n/k³ as well. So this will imply the hardness for the streaming setting, but before getting to that point, let me briefly go over some of the works in the streaming setting. The first one is a 1/4 approximation that keeps k elements as in the messages, basically. So the length, the size of the memory is basically O of k. Then it was improved to 1/2, while the size of the memory over epsilon log k, so the memory that it uses is k over epsilon log k. And recently, the log k in the factor in the memory. And in a very recent work, Huang et al. Shows a k over 2k minus 1 approximation, so slightly better than 1/2. You can think of it as 1/2 plus 1 over k, basically. But the memory is exponential with respect to k, but still clear relationship with n. There are two lines of research from the inapproximability point of view, one for weak oracle and one for general oracle. For the weak oracle, it's known that 1/2 is tight and one cannot achieve better than 1/2. Recently, again, Huang et al. Showed that 0.58 upper bound for the general oracle as well. And in this work, we show that for the general oracle, 1/2 is also tight. What's the difference between weak oracle and general oracle? In the weak oracle, the algorithm can only query the value of function f for the sets of size at most k. But in the general oracle, there's no assumption, and the algorithm can query the value of any set S. So the size is not an issue. Any size is okay. So basically, we extend our k-player string as well. Let me just briefly explain the differences between general oracle and weak oracle from the computational point of view as well. So if we just focus on the two-player, in this work, we show that 2/3 is the correct answer. But for the weak oracle, it was known that 1/2 is the correct answer. So the computational power between these two oracles are different. So a general approach for showing inapproximability results in the streaming setting is as follows. We want to design a family of instances that have two properties. First of all is the value gap. This means that the value of optimum solution should be a factor x bigger than the optimum solution from the entire universe, removing the optimum element. So if we remove the opt, we expect the optimum solution remain to be a factor x different from the value of the optimum solution. So in this work, because we want to show a 1/2 hardness, we want this factor to be 2, basically. And the other one is indistinguishability. Let me just focus on a more more general version. That is, the ith element should not be able to distinguish between the elements that it has in the sense that whether they're part of the opt or they're not part of the opt. Given all the elements from the first player to ith player. So if ith player knows all these elements, still he should not be able to distinguish which of the elements that he has is part of the opt and which ones are not part of the opt. Having these two properties together for a family of instance will result to a 1/2 hardness. And that's basically intuitive because from the second one, we know that any algorithm cannot basically pick the opt element. It's very unlikely, very hard. It's basically impossible to pick the opt elements because we have a lot of elements, and unless you pick basically most of them, you don't pick the optimum one, and you cannot distinguish which one is the opt one to pick. And from the value gap, we get that, okay, if it doesn't pick, a solution does not have any element from the opt, the value of it is half the value of the optimum solution. So we get the half hardness that we want. Okay, so let me first describe the 1/2 hardness for the weak or in the weak oracle setting. So the first player has many elements, each of them worth opt over 2k, and the second player has a big element that worth opt over 2. There are specific k elements from the first player that are independent from the big element. So adding them to the big element just gives the contribution of their size, basically adds opt over 2k, and adding I of them at I times opt over 2k. And we have many blue elements that adding them to opt the big element does not increase the objective function at all. So they're fully overlapping the big element. So now the optimum solutions is basically all the green ones. From now on, the optimum solutions are the green ones, and the blue solutions are the ones that are not part of the optimum solution. So it's clear that the value of the optimum solution, the green ones, is opt, because you have basically k of them that worth opt over 2k and one that worth opt over 2, and the value is just their summation, so it's opt. So the value gap is as intended, is the 2 that we wanted. But what about indistinguishability? Do we get that or not? So let's say one can ask for the value of the sets of size at most 2k, for example. Then subsets of the blue guys of size 2k, they will give opt over 2. The value is opt over 2. And the reason is that, okay, they are all overlapping with the big one, so their union is not more than the big one. So their value is not more than opt over 2. On the other hand, if you pick the k opt guys and the k guys from that are not part of the opt, we basically get opt over 2k times 2k, we get opt. So it's possible to distinguish between opt elements and the ones that are not part of the opt. But in that work, the authors achieved indistinguishability by not allowing queries of size more than k. And we can see that if we only let the size of the queries be k, it's not possible to distinguish between them, because the value of any set of size k is opt over 2. Okay, so why can't we just extend these ideas to the general OLACAP? The first reason is that, okay, as we show in this work, the 2/3 is the correct answer for 2-player in the general setting. So of course, we have an algorithm that gives a 2/3 approximation, so 1/2 cannot be extended. And also, it's known that if any solution, if an input has a big element of size opt over 2, then there is possible to achieve algorithms that work more than 1/2. So because of these two reasons, at least one cannot hope to extend this idea. So now I will introduce the instances that we build. I go step by step, and each instance will improve the previous one. And I will talk about the indistinguishability and value gap properties. And at the end, we hope to achieve the desired value gap of 1/2 while the instance is still indistinguishable. Okay. So let's say we have a space of size opt. For the first player, we randomly select many elements of size opt over k. So basically, we just sample elements, and we sample a lot of them, and it's the elements that we give to the first player. So first of all, and we choose one of them to be the optimum solution for this player. So first of all, it's clear that it's indistinguishable, because everything is chosen at random, and we cannot distinguish which one is the optimum one. But what about the value gap? For value gap, we should consider more players. The second player is the instance for the second player is very similar to the first player. The main difference is that we remove the part of the opt that the green element of the first player is covering and sample from the rest of the universe. So we have the entire universe. We remove the part that is for the green element of the first player, and we just sample from the rest of the elements. And again, we sample many elements of size opt over k. And choose one of them to be the green one for the second player. Basically, recall that the green ones are the ones that are part of the optimum solution. So we still get indistinguishability, but what's the value gap? Now it's clear that the green elements, if you add them up, you get 2 opt over k. And basically, any two other elements does not give 2 opt over k, because they are chosen at random and they intersect with each other. For the third player, it's similar to the second player. We remove the optimum part of the first player. We remove the optimum part for the second player. Basically, we remove this green part, and then sample from the remaining and choose one of them to be part of the opt. Again, For each three elements, the three green ones, the value is 3 opt over k because we removed and then sampled. But for any other elements, they intersect with each other, so the value is it's less than 3 opt over k. So we are starting to get some value gap. For the pth player, it's exactly the same. Remove the green parts of the first p-1 element, sample many elements from the remaining universe, and choose one of them to be part of the opt. If we keep doing like this, we can show that if an algorithm picks one element from each player, from the blue elements of each player, it achieves opt over 2 for large enough k. I just put the formula, but just trust me, it will be opt over 2. So, okay, if we pick the green element, we get opt. If we get one element from each player, we get opt over 2, but do we get the value gap? And the answer is no. Why? Because if we choose k elements from the first player, from the blue elements of the first player, it's just equivalent of choosing subsets of size opt over k uniformly at random from the space, and the value would be 1 minus 1 over e times opt. So we don't get the value gap. Then we have to move to the second idea that we have, that the size of the elements for each player should be different, and it increases over time. So for the first player, it's smaller than the second player, and so on till the kth player. We still have the indistinguishability because everything is, again, chosen at random. And now, by choosing the sizes carefully, we can ensure that the green elements still work opt. If you choose one element from each player, you cannot achieve better than opt over 2. But does this approach help, at least for the first player? So let's say the size of the elements for the first player is opt over 2k. Then if you choose k of them, because the size of each of them is less, we expect to get less as well. And we can show that we get something like 0.4 times opt. So it's actually helping for the first player. But one might wonder that, okay, because the first player, the size of the elements is smaller, for some players it should be bigger. But, and then we pick k elements from that player, and we should get better than opt over 2. The key observation in here that the space is also shrinking over time because we are removing the opt part. So the amount that they intersect will increase, and we can basically achieve that for all the players. If you pick k elements from them, you don't get better than opt over 2 as well. So basically, we show that if you pick all from the first player, you get at most opt over 2. If you pick from one element from each player, you get opt over 2 as well. And it's more involved, but we can show that for any mixture of them, we don't get better than opt over 2 as well. Therefore, we get the desired value gap and this indistinguishability result that we wanted. And basically, this will result in the 1/2 hardness for the streaming setting. So let me give a quick summary of the results that we had. We explained that we discussed the two-player setting and showed that the correct answer is 2/3, and we showed that it will give the 2/3 approximation for the robustness in the robust setting as well. We extended to k-player and showed that 1/2 is tight, which also implies that in the streaming setting, one cannot achieve better than 1/2. So let me explain a couple of open questions in here. So for the matroid constraint, it's known that 1/2 is tight, but the algorithm uses exponential memory with k. And among the algorithms that use polynomial memory, it's not the best known approximation ratio is 1/4. So one natural question to ask is that what's the correct answer if we are only allowed to use polynomial memory? And also, what results can we get if we allow two-way communication? This will have application in multi-rounds in the streaming setting. The other questions, of course, is that, so for robustness, we show that 2/3 is achievable, but what's the correct answer? Is 2/3 tight, or one can improve it? And what's the best that we can get in the with the polynomial running time? Thanks for watching this video. I hope to see many of you in the discussion section. Have a good day.